Yeah, in German. Okay, good. Yeah, now it's starting the recording. So good.
Okay.
Um, yeah, good. Then may I announce our today's speaker? It's my pleasure to have Liangyi Zhao here from the University of New South Wales in Sydney, Australia. And he talks about a topic which is related to earlier talks which we have seen, namely about moments of central values of quartic Dirichlet functions. Okay.
Well,
Hmm?
thank you very much, Stefan. Thank you for the invitation. I'm happy to be here and giving this talk. So let's see. I guess you can also see the slides progressing. Okay. Okay, so that's the outline of the talk. I'll give some introductions, then statements of results, sketch the proof a little bit. Time permitting, I'll also talk about this large set of inequalities for quartic characters. Well, anyway, so let's start. I'm to understand that not everyone here is a number theorist, so I'll try to be slow. Well, I'll try to explain things slowly. Okay, so let chi be a Dirichlet character of conductor Q. Well, okay, so if you don't know what that is, it's basically a homomorphism from Z mod Q Z star, and you extend that to periodically to the entire set of the integers, and the conductor Q. Well, it's basically the modulus of this character chi. Well, it said conductor because we want to assume that this chi is primitive. I mean, if a function is periodic of period q, then that function is also periodic of period any multiple of q. So we call a character primitive if primitive of modulus q if q is the smallest period, basically, and the conductor of a character is basically the modulus of the primitive character that induces this character chi. All right, and the Dirichlet function that's associated with chi is defined here. So L as chi equals sum n from 1 to infinity, chi of n over n to the s. S here is the variable, right? And if we assume that the real part of s is strictly larger than 1, well, yes, strictly larger than 1, then that sum converges. Absolutely. And so I do have a well-defined function there. And so I said that chi is a Dirichlet character in mod q, or of conductor q. So there's a character that's trivial, which is basically defined to be 1 for every integer n. And that character is called the principal character or the trivial character. And if this chi is this trivial character, chi sub 0, then we have the Riemann Zeta function. So the Riemann Zeta function is basically the same sum, except upstairs of the summons, instead of chi of n, you have 1 there. And the sum converges whenever the real part of s is strictly larger than 1, and you have that Riemann Zeta function. All right, and some important properties of these functions, Dirichlet functions, include they have functional equations, and via these functional equations, these functions L as chi can be extended meromorphically to the entire complex plane. So as the function stands now, it's only defined for the real part of s strictly larger than 1. So because of this functional equation, which I'll talk more later about that. Because of this functional equation, the values of s to the left of for s's with negative real parts can also be defined, and therefore you have this meromorphic continuation. And in fact, if chi is not a principal character, if chi is not always 0, if chi takes some values other than just 1, sorry, I might have misspoke. If chi is not always 0, if chi is a character that's not the principal character, then in fact this sum converges for the real part of S strictly larger than 0. So this functional equation, I'm not going to write it down. You see some version of it later. So what this functional equation does is that it relates the value of Ls chi to those of L of 1 minus x, 1 minus s chi bar. Chi bar is the complex conjugate of chi, and 1 minus s is, well, 1 minus s. So if I know what Ls chi is for real part of s larger than 1, and then by this functional equation, I will know what the what Ls chi is for real part of s less than 0. Okay, and because of this functional equation, I mean, s is related, well, the function value at s is related to the function value at 1 minus s. It makes sense to call s equals to 1/2 the central point in this setting. And, well, it turns out the values of a L function at this central point, it has a lot of arithmetic information, depending on what kind of L function you're looking at. All right, so okay, so before I move on, perhaps one more comment here. I mean, we know elliptic curves, and these elliptic curves can have well, you have L functions associated with elliptic curves because of a different normalization. The central point for those L functions is at s equals to 1, and if you know the Birch-Swinnerton-Dyer conjecture, you know that the order of vanishing of the central value of that L function of elliptic curve L functions, that has a lot of arithmetic information. That order of vanishing is conjectured, at least in general, conjectured to be the rank of the group of rational points on the elliptic curve. So on the one hand, we have a very analytic object, the order of vanishing, and on the other hand, we have a very arithmetic piece of information, rank of some group and the order of vanishing. I mean, so the point here, the upshot here is this central point, especially the order of vanishing of this of L functions at this central point, can have a lot of arithmetic information. Right. So the average value of L functions at this central point over families of characters have been studied extensively. Right, and particularly families of characters with fixed order. So, well, I started this talk by saying that chi is this started out its life as this homomorphism from Z mod Q, Z star to C. So it's a homomorphism. Well, it can be thought of as a homomorphism on a finite group to C. So all of these homomorphisms, they form a group. They form a finite group as well, and they have finite groups. Well, they form a finite group, so they have finite orders. So this order K, well, as here. So characters of a fixed order. So chi raised to the K is the trivial character, or it's the principal character for some fixed K, for some fixed natural number K. So in this direction, for K to 2, so if K is 2, then you got quadratic characters. So these characters only take on values 1 minus 1. So this problem was studied first by Utila and then by Sanderarajan. And for k equals to 3, this was studied by Stefan and Matt Young for Dirichlet characters. And Wenji Luo also studied the same problem, or rather a similar problem for k equals to 3, but with Hecker characters. Well, Hecker characters aren't Dirichlet characters, but they're related, as we will see later if I have time. So they can be thought of as homomorphisms on some extension ring of Z. So right. So I'll go to the next bullet point before making any comment. So a conjecture that goes back to Chawla says the following. An L function is never 0 at the central point. A Dirichlet L function is never 0 at the central point for any primitive character chi. Okay, so in fact, there's a folklore conjecture which says, which is along the same line as this conjecture, which says that if you have any L function, unless there's a good reason for the L function to be 0 at 1/2 or wherever its central point is, it's never going to be 0. Well, what do I mean by a good reason? What I mentioned earlier, this order of vanishing can be related to the rank of the group of rational points of an elliptic curve for elliptic curve L functions. So if you know an elliptic curve has positive rank, then that's a good reason for that L function to be 0 at the central point. So there's at least one other possible reason. If the root number is -1 or something, then the L function is necessarily 0 at the central point. That's another good reason. So unless there are these good reasons, an L function should never be 0 at its central point. That's what's called, I think that's what's called the folklore conjecture. It's a sort of not really mathematically precise, but it can be summarized as, unless there's a good reason for an L function to be 0 at its central point, it's not 0 there. So one motivation, therefore, to consider these moments is to address this conjecture of Chawla. As mentioned above, those results that I mentioned above by Utila, Sander Origin, Bayer, Yang, Luo, they all have been used to prove non-vanishing corollaries for the families of L functions under their consideration. I should especially highlight the result of Sander Origin for k equals to 2, because what he managed, well, that was sort of a pioneering, a pioneer paper, because what he managed to prove was a really high percentage of Dirichlet L functions attached to real characters are not 0 at 1/2. And if I remember correctly, the percentage was over 90%, right? I think 93 or something. Oh, possibly even higher. All right. So our first result is the following. So let W be a function from 0 to infinity to R, and it's smooth, so it's infinitely differentiable. It's got compact support. And let's call its Fourier transform W hat. So we assume the Lindelöf hypothesis. Well, okay. If you don't know what the Lindelöf hypothesis is, it's basically a bound for the L function in the critical strip, or in a strip of on the complex plane for complex numbers with real parts between 0 and 1. well, it can be simplified a little bit. I mean, it's really about the growth of these L functions on the line s equals to, well, real part of s equals to 1/2. So assuming the truth of that hypothesis, we have the following. So we're looking at the central values of these L functions at 1/2, right? And this W here is just some weight function. Because it's compactly supported, we're basically looking at these L functions attached to chi, whose conductor is about size capital Q. Right? So we're looking at the average values of these quartic L functions. So chi to the 4 to the 4th power is chi sub 0. So we're looking at the average values of these quartic L functions at 1/2 over, well, the quartic characters, and also running over the moduli of chi. And this average value satisfies this asymptotic formula. So it equals to some constant times Q. Q is this Q here, which is the approximate size of the moduli of chi, and W hat of 0. So the W hat is the Fourier transform of W. So the Fourier transform of W evaluated at 0. C is just some positive constant, which can be computed. There's a formula for it. It's a long and complicated formula. So it's basically some number multiplied by Q. W hat of 0, that's just some other number, right? So number multiplied by Q plus big O of Q to the 9/10 plus epsilon. And there's a matter of notation here. So we're averaging over quartic characters. So chi to the 4th is chi 0. Well, okay, so we only want to consider quartic characters, right? So we want to exclude the trivial character. I mean, the principal character raised to the 4th power is also the principal character, and also any real character, any character of order 2 when you raise it to the 4th power, it's also the real it's also the trivial character. So this notation here with asterisks here, this restricts the sum to characters that are primitive and whose when you square it, it's also primitive. So I'm really restricting myself to quartic characters. I want to exclude real characters, right? So that's the theorem here. The average value here is basically some constant multiplied by Q plus some error term, which is small compared to the main term, of course. And additionally, we also have the following second moment result. So, well, second moment means, well, okay, I'm squaring these L functions. So I'm looking at the average values of these L functions plus IT. And now I can actually look at the values of these L functions on the line. Real part of S is 1/2. So over here, I don't have an asymptotic formula, but rather I have an upper bound. So Q to the 7/6 plus epsilon multiplied by this 1 plus T to the 1/2 plus epsilon. So I have an upper bound for this this average second moment. Well, or rather just this second moment here. So the proof of this second moment result relies on a large Sevier inequality for quartic characters, which will be discussed later if I have time. All right, so and the second moment result for quartic Hecke characters can also be proved. So instead of chi here, I may have some other average value over some Hecke characters. As I said earlier, I mean, a Hecke character is a generalization, well, or rather an extension of a Dirichlet character. I mean, instead of looking at homomorphisms from Z mod Q Z star to C, we're looking at homomorphisms from, say, some integer ring. Rather, cosets over the quotient ring, over the quotient ring of some integer ring, right? All right. So I said earlier that one is motivated to study these moments because of Charlotte's conjecture. So we have the following non-vanishing corollary. So assuming the truth of the Lindelof hypothesis, there exist infinitely many primitive Dirichlet characters of order 4, such that L1 half chi is not 0. So more precisely, we have the following more quantitative result. So the number of such characters for which, so primitive quartic characters chi, for which L1 half chi is not 0, and the conductor of the character is at most q. That's at least, well, greater than, which means is greater than equal to some constant multiplied by this number here. Well, this quantity here, q to the 6/7 minus epsilon. All right. So once you have those results, moments results, the first moment and the second moment result, then this corollary comes rather easily. So this corollary follows easily from those theorems by just using Cauchy's inequality, because well, I mean, you can. It's pretty easy to set up. I mean, if you have a well, you can just set up the moments. For example, just looking at the first moment here. I mean, if L1 half chi is 0, then there's nothing here. So this thing on the left hand side is the same as if I was just summing over L1 half chi, for which L1 half chi is non-zero. And then I can just apply Cauchy's inequality to the left hand side here. So one factor in the Cauchy's inequality, I can just let it to be 1, and on the other factor, the other factor, I can just have L of 1 half squared, L of 1 half chi squared, and then I can just apply. This second moment result as an upper bound, and the first moment result as a lower bound for the whole thing, and then I'll have a lower bound for the number of characters for which L1 half chi is non-zero. So it's a pretty easy corollary once you have the moment results. All right, so let's move. So let's have a sketch of this first moment result. Well, I'll give a sketch of this proof here. So let this M be the left hand side of the thing on the left hand side of in the equation in the theorem. So basically, this thing, the thing on the left hand side here. Sum over q, then sum over chi, L1 half chi, WQ over q. Right? So let that be the left-hand side. We want to prove this asymptotic formula. So the first thing that I want to do to that M, which is the left-hand side of that equation, is to apply something that's known as the approximate functional equation. So what it does is the following. The approximate functional equation transforms, well, it's about, first of all, it gives values or approximate values for L of S chi, where S lies in the critical strip. Well, in other words, if S has real parts between 0 and 1, and 1 half is certainly between 0 and 1. So if you apply this approximate function equation, which gives approximate values of L of 1 half chi, you end up with these two sums. So the approximate function equation is really the following. So it approximates L functions for S with the real parts between 0 and 1. And what does it approximate it with? Well, it approximates the approximate functional equation approximates these L values with the following two Dirichlet polynomials, if you will. So Dirichlet polynomials are really just things of this form. So we have chi upstairs, and then we got some m to some power downstairs, and then we sum over m. So this sum over m, that can be thought of as a Dirichlet polynomial. Remember, W has compact support, so that this goes from m goes from 1 to infinity. So, but it's really a finite sum because W has compact support. All right. So the values of L1 half chi is approximated by these two Dirichlet polynomials. So okay. Remember, this chi comes from before. This W weight function comes from before. What is this V here? Well, this V, it has some gamma factors. So if you're familiar with the subject, this is pretty standard. But if you've never seen this before, the functional equation of an L function, of a Dirichlet L function, or in fact any L function, will have a bunch of gamma factors. It will involve a bunch of gamma factors. So remember, the functional equation of the L function relates L of s to L of 1 minus s. Well, there are a bunch of other things in this functional equation. Among other things, there are these gamma factors. And so just think of these V's as gamma factors. And okay, this W are those weights which you have from before. This epsilon chi. Well, this epsilon chi is what's called the root number of LS chi. So I'll talk more about this later, time permitting. But right now, you can just think of this as some complex number of modulus 1. Later, we'll see that we'll have more information on this epsilon chi. It has Gauss sums in it. Well, I'll talk more about that. And also this capital A and capital A sub q and capital B. Well, the product of these two things must be q, right? So that feature or that condition comes from the approximate functional equation. All right, so hit the L1 half chi with the approximate functional equation. We have these two sums. Well, so let's look at M1 first. Well, M1. Well, in fact, both M1 and M2 will be subject to this transformation, and this is an important lemma. What it does is the following. It transforms, or rather, it recasts the character chi, Dirichlet character chi, as some other character, some Hecke character. So instead of looking at this character on Z, we look at this character on some other ring of integers, as the Gaussian E integers, rather. So a primitive quartic character of conductor Q with an odd Q, such that its square is also primitive, is of the following form. It can be rewritten as a Hecke character. So chi sub n, and this thing goes from m to m over n sub 4. For some n, for some Gaussian integer n, that's congruent to 1 modulo 1 plus I cubed. And the norm, the norm of n as a Gaussian integer is q, and n is square free. It's square free in Zi, and it's not divisible by any rational prime. So that's an important lemma. And of course, this m over n4, that's the quartic symbol in the Gaussian E integers. So these Hecke characters are basically extensions of Dirichlet characters. Instead of working over Z, I'm working over Zi. What this lemma does is that it rewrites this those characters, chorded characters chi, as basically these chorded symbols in Zi. So what this does is basically it transforms those Dirichlet characters to Hecker characters. And so once we made this identification, so this the chi's will simply become chi sub n. Then we can rewrite the sum that we had above. I mean, from the previous slide as this. So m1 can be rewritten as m1 plus m1 minus, where m1 plus and minus is written here. So if you take a look at this, chi n of -1, well, because chi is a character, or it's a homomorphism, if you will, if you want to restrict yourself to quotient rings, then this chi n of -1, this thing is either 1 or -1. If chi is chi n is 1 and -1, then that's an even character. If it's -1, then it's an odd character. So if you take a look at this plus or minus sign, or rather this decomposition of m1, basically these two terms basically breaks up the character chi sub n as even characters or odd characters. So for positive, if I'm looking at m1 positive, then this 1 plus chi n -1/2, that is 1 if chi is even, and it's 0 if chi is odd. And for minus signs, from m1 minus, I get a 1 if chi is odd, and I get a 0 if chi is even. So this is m1 plus is for even characters, m1 minus is for odd characters. All right, so breaking up those two things, and this chi double prime is basically it basically restricts these n's, restricts the n according to this lemma which I had earlier. So n runs over a square-free Zi, square-free things in Zi, and it doesn't. N has no rational prime divisors. So this lemma, which I have here in that bullet point, together with breaking up the sum according to whether the character is even or odd, breaks the sum m1 into m1 plus plus m1 minus. All right, so let's keep on going. So m1 plus and m1 minus can be handled in similar ways. So we'll just focus on the former. So we apply some transformations to rewrite this this sum sigma double prime, and apply Millenian inversion to this function v times w here. Well, so so over here I have the Millenian inversion. So upon applying Millenian inversion, we end up with an expression of this form. I mean, if you're familiar with the proof of the prime number theorem, it's precisely that. I mean, we apply Millenian inversion, and we transform the sum over the Fomango function into some integral involving the Riemann Zeta function. It's basically the same method here. So we'll get an expression of this form. So well, these variables D and L, they come from the transformations which were done earlier. I mean, these transformations basically takes care of the conditions that we have on this sum. I mean, takes care of the conditions on the sum sigma, or rather summation double prime. So these variables come from there. F tilde is the Millenian transform of V and W, V times W, because I'm applying Millenian inversion. So that's why I have this. And we know good bounds for f tilde, because we have good bounds for v. I mean, v is just the well, a function involving gamma functions, well, different kinds of gamma functions, and w is this smooth function with compact support. So we have good bounds for f tilde. And ls psi md squared. Well, okay, because well, if you go back, we have this sum here over m with this Hecker character chi sub n. So as I said earlier, this is the same method as the proof of the prime number theorem, where the explicit formula. So once you apply this Mellinian version, because of that sum over characters, you end up with the integral involving the corresponding L function. So if you have the Von function, you end up with zeta prime over zeta, and since we have that chi, that Hecker character chi sub n, we'll get the corresponding L function. So there'll be a bunch of other things. There are a bunch of other arithmetic restrictions or arithmetic things in this computation. So that's why instead of simply the Hecker L function of chi sub n, you have the Hecker L function of psi sub m d to the fourth. You will need reciprocity here, among other things, and there are other arithmetic restrictions. So that instead of simply chi sub n, you have a different character. But in any event, that different character is not very different. It's still a quartic character. It's still a quartic symbol, and the modulus of that quartic symbol is md to the fourth. So then, again, if you remember the proof, or if you remember the proof of the explicit formula, well, what do you do next? Well, it's sort of a standard thing in analytic number theory. You start moving the contour. So the contour earlier is over this line with the root part of s equals to 2. So you can start moving this contour. And we can move the contour among other things. Well, one half, the line at real part of s equals to 1/2 is well, it's a convenient line for many reasons. So we'll move the contour to that line, the real part of s equals to 1/2. Well, so do we pick up any residues? Well, we will. If you are familiar with the theory of L functions, if you have the trivial character or the principal character, then you'll have a pole at s equals to 1. And so the character of the L function to which the L function is attached to is the psi d m to the fourth. So 1 is that principal. Well, if it's principal, then we do have a pole, and we'll need to compute residues. And if it's not principal, then it won't have a pole. We don't need to worry about residues. So 1 is this the principal. 1 is this the principal character. So remember the I said earlier, this character psi is a quartic symbol, and so you will have a principal character if m is a perfect fourth power. But I mean, it's a quartic symbol, and md to the fourth. That's the modulus of that's that character. And so if m is a fourth power, then you basically have you basically have the principal character. So whenever m is a fourth power, you will get a pole, and you will need to compute residues. And once you compute these residues, that will give rise to the main term in the theorem. Remember, the main term was CQ W hat 0, right? So that will give rise to the main term there for these principal characters for which m is a fourth power. So if psi md to the fourth power is not principal, then we'll just bound the expression. So the expression, remember the expression is this. This can be handled. F tilde, I said earlier, we know good bounds for F tilde. And so in order to bound the whole thing, there are more sums on the outside, but those things are more or less trivial. The important thing really is the L as psi. That's really the only important thing. And so at this point, we'll invoke the Lindelof hypothesis here to bound L as psi. Remember, I said earlier that the Lindelof hypothesis gives a bound for these L functions on the line, a real part of S equals to 1/2, and that's exactly where we are when we've shifted the contour of the integral to the line, the real part of S equals to 1/2, and we apply the bound that's given by the Lindelof hypothesis for these L functions, and then they're just cleaning things up. Then we'll end up with the error term that we have in the theorem. So the known bound, I mean, clearly we still call it the Lindelof hypothesis. So in other words, it's still open. We don't know the full result of the Lindelof hypothesis, but we do know some partial results. Those are called subconvexity bounds. So okay. So I there's a typo here. Are not good enough for an asymptotic formula. I'm missing the important modifier there. So the known bounds are not good enough. I mean, there's some not that's missing. I mean, if they are good enough, then we don't need to invoke some unknown conjecture. So known results, known bounds in this direction are not good enough for the asymptotic formula that you have earlier. So this takes care of M1. So for M2 is a little bit more complicated because it has the root number. Remember, this root number is this epsilon chi. All right, so that's more complicated. So after some transformations that are similar to those for formula L1, we end up with this bound, with this sum. So we still have this W here, which is the weight, which is always there, which is there from the very beginning. Chi is this character, chi bar, because it's the other term in the it's the second term in the approximate functional equation, and square root of the norm of n. That's basically the square root of m there in the approximate functional equation. And this g here, this is probably the first time. Well, this is the first time that appears. So what is that? Well, that is the following. Well, again, L comes from the transformations before, and this G is a Gauss sum in the Gaussian integers. So the root number, so where does that come from? I mentioned earlier that this root number involves the a kind of Gauss sum. So this root number epsilon chi contains the classical Gauss sum tau of chi. I mean, this tau of chi is the classical Gauss sum over the E integers, and these classical Gauss sums can be related to these extensions of the classical Gauss sums, g of x. So because chi, because of this epsilon chi was present in M2. So this tau of chi is present in M2. Then this tau of chi is related to this g of n by classical formulas. So we end up with an expression here, or an expression that's like that anyway. Well, okay. Then in order to deal with this, we use a result of Patterson. Well, that's the key input here, which is a very well, it's a classical result, and it's a very useful result. So what does this result do? Well, what does the result say? So Patterson studied the analytic behaviors of of Dirichlet series involving Gauss sums and Hecke characters. So if you take a look at this expression, it's precisely what we need, right? You got Gauss sums here, you got Hecke characters here, and well, it's a Dirichlet polynomial that you have here, right? Or Dirichlet series or Dirichlet polynomials, because this W has compact support. It is really a Dirichlet polynomial. So that expression on the previous slide is precisely the subject of the result of Patterson. So you got your analytic behaviors of that Dirichlet series or Dirichlet polynomials. So using Patterson's work as tools or roadmaps, we are able to bound the above sum, the sum on the previous slide, and that will give us the results that we need, or the result that we want. All right, so that concludes the first moment proof. Let's go to the second moment, and that's that expression that we want to bound for the second moment. So I say over here, the bound for the second moment is easy if you have the correct tool, if you have the right tool. So we need to bound this. That's the expression, right? We are looking at coordinate characters. We're looking at squares of these L functions, and we're summing over characters Q, characters modulo Q. So again, we can apply the approximate function equation, and we're led to bound this. All right, so if you just apply the approximate function equation, so remember I said the approximate function equation approximates the values of L1 half chi, or values of L functions in the strip for which the real part of S is between 0 and 1. So over here, I certainly have, well, 1/2 plus IT, that's certainly within that strip, if T is a real number, of which it is. So it approximates these L functions, the approximate function equation approximates these L values using Dirichlet series, which is precisely what this is. Well, okay, so if you take a look at that, again, we know good bounds. Well, we know what these V's are. These V's are things involving gamma factors. And chi's are these characters, m to the 1/2 plus IT. That's from before, from the approximate function equation. So that's precisely something for which we can apply the large sieve inequality for coordinate characters. Okay, so you just do that. Well, so what is the large sieve for coordinate characters? So in brief, that's what this is. The large sieve inequality for coordinate characters is precisely this theorem here. So A is a sequence of complex numbers. We have the following. So we're summing over Q, and then we sum over coordinate characters. So characters whose fourth power is trivial, but whose squared is not. Then we have this inner sum, A sub n. These are arbitrary complex numbers, and characters chi of m. So if you take a look at this expression on the previous slide, this is precisely this inequality on the next slide precisely gives a bound for this expression here, or is something. I mean, we need to divide Q and M into dyadic intervals and so on, but that's not a big deal. After some simple transformations, this thing here on this slide will become something that's of this form. So then you just apply this bound here and figure out which one of these things in the minimum is the best for the ranges that we're working with. It turns out that this term Q to the 5/4 plus Q to the 2/3 times m, it turns out that is the best term, and that's the smallest thing in the minimum. So you just apply this this bound to the sum on the previous slide. Then you end up with the bound for the second moment. All right. So in the remaining maybe 5 minutes or 8 minutes, 7 minutes. Well, I don't know how far I can get, but let's talk a little bit about this large sieve for coordinate characters. As I said earlier, the second moment result is easy to prove if you have the right tool, which is precisely this large sieve with coordinate characters. Well, okay, so let's talk a little bit about the large sieve. Well, which is, well, this goes back, 70 years from now, 70 years in the past. Linux was the first persons to study the large sieve, although back then it was somewhat different. He was studying the distribution of quadratic non-residues, and this theory has been studied and perfected by many, including Linux, Reni, Roth, Bambieri, and Gallagher, and Davenport, and so on. You will have noted, let's see, 2 Fields medalists in that list of names. So nowadays, the term large sieve it really refers to a sort of a mean value estimate for character sums. And so the multiplicative version of the result can be expressed as the following. So that's the large sieve inequality for multiplicative characters. So again, AN is a sequence of complex numbers, and chi is is a character. And so we have this average value twisted by of average character sum twisted by these ANs. Then we average over the characters, primitive characters, mod q. Then we average over q. This q over phi of q, you can think of that as 1. Well, you can think of that as 1 if you want. Just waving your hands up and down. So this is bounded above by this quantity, q squared plus n minus 1, multiplied by the square of this L2 norm of this AN here. Where star here, this says chi runs over primitive characters only. Well, okay, I don't have enough time to go into the details because this is a very useful result. Among the things that probably the most useful, the best known use of this result is what's called the Bambieri-Dinogradov theorem. So what it is, I may not have time to discuss the full beauty of this result, but we can at least try. I mean, if you take a look at this psi x a q, we're basically looking at all primes. I mean, think of this lambda n as the prime detecting function. So this is log of p as if n is a prime power, p prime power n is 0 otherwise. So we're looking at all n's that are congruent to a mod q. So we're basically looking at all primes that are congruent to a mod q. So primes in arithmetic progressions. And this is, well, think of log of p as 1 or something, just to make your life a little bit easier. So we're basically looking at a number of primes less than x that are congruent to a mod q. That's basically what this is. And the result here, we're basically looking at this number of primes congruent to a mod q. Then we subtract x over phi of q. That's actually the main term in the prime number theorem for arithmetic progressions. So the error term here, so this basically is the error term in the prime number theorem for arithmetic progressions, and we're taking a max here over a. In fact, well, there are a couple other maxes you can add in as well. Then we're taking the average over these error terms, where the average runs from 1 to basically the square root of x. This is some log power. The sum, or rather the average of these error terms is at most x over log to the power a of x. and the implied constant here depends on A. So that's the best known, perhaps the best known application of the large set inequality for for multiplicative characters. And in fact, this theorem goes into is an integral. Well, it's an important ingredient in Maynard's proof of bounded gaps between primes, right? Which was even that result is 8 years old now, I think. Well, okay, so 2 can be thought of as an average version of the generalized Riemann hypothesis because, our GRH says that this error term is bounded above by essentially square root of x. And, but if you take a look at this, if each one of these is square root of x, each one of these error terms is square root of x, and we're adding up square root of x of them, then we expect the sum to be less than x, right? Square root of x times square root of x is basically x. So this is an average result, so it's not as strong as GRH, but GRH basically implies this. It's a result whose quality is on par with GRH. All right. So and in applications, it's this Bambieri Dinogradov theorem is often enough to replace GRH in applications. And a conjecture of Elliott and Halberstam says that not only can you go all the way up to square root of x, you can in fact go beyond. You can go to q to the. You can average over q to the x to the 1 minus epsilon. I see that I'm running out of time. So there are many directions to extend the large set inequality. One direction is to restrict over moduli, which is studied by many authors, including Stefan and myself. And another direction, another extension or direction of study for large set inequality is to restrict the order of characters, which clearly I alluded to. Well, I've been talking about this, right? I mean, we can restrict ourselves to characters of order 2, order 3, and of order 4, right? So Heath Brown was the first to study this subject. So he proved this mean value theorem for character sums for quadratic characters, right? So yeah, so I'm out of time. So using his method, Heath Brown's method, we can also develop large set inequalities for cubic characters, which Stefan and Matt Young did. And this method is also applicable to large set inequalities for quartic characters. So here I have this average value for quartic characters, and this was improved by Blumer et al. Blumer, Goldmacher, and Louville. And so using Heath Brown's method, which is a beautiful method, but I don't have any time to go into. I mean, I'll just say this. I mean, in a very strong field, I mean, there are many beautiful results in analytic number theory, and I must say that this result of Heath Brown for large set inequalities for real characters, it must be among one of the best results in analytic number theory. In my opinion, anyway. Probably Stefan will agree. So in my slides, I sketched the proof of the large set inequality for quartic characters, which uses the method of Heath Brown. It's a very beautiful method. The recursive treatment of those sums, which I won't have time to go into. So once you use this beautiful method, allegedly beautiful method, to prove this large set for quartic characters, and you apply that to the moments of L functions, and then you end up having the upper bound for the second moment. All right, so I see that I'm out of time, so I'll just go to the very end. Thank you very much for your attention.
Yeah, thank you very much for the very nice talk.
Thank you.
Yeah, so with regard to this Large C for real characters with Heath Brown, I agree. Very beautiful paper. One of the most beautiful papers I know in analytic number theory.
Yes, yes. Okay, any questions? I suppose I'd be happy to answer any questions if you have any.
I myself are familiar with your work, so I have at the moment no question.
Yeah.
We are anyway in touch. Yeah.
Yeah, I didn't. Well, I mean, I'm sure you're familiar with the methods here, even though I didn't go into details in many. Well, on everything.
Yeah. By the way, that was very good that you adjusted your speed to the audience, because we are not. I mean, the audience is not consisting entirely of number theorists.
I mean, the slides I skipped at the end, those are very technical. So
yeah, that was good. Yeah, was very nice.
Okay.
Very accessible.
Yeah. Okay. Thank you.
Accessible. Sorry.
Yeah.
Yeah. Are there questions from the audience?
Oh, it's actually my first time giving a talk like this. It's
Oh, really?
I mean, I've talked like this before, but not presenting at a research talk.
Ah, I see. First lockdown talk.
Yeah. I've run conferences this way, but not being a speaker myself.
Yeah. But it went smoothly, technically also. So you did well. But you are online teaching, right?
Well, I'm on sabbaticals right now, but yes.
Okay.
Once that's over, I'll be teaching online.
Yeah. Na gut.
Okay.
If there are no questions, then I suppose when you have questions later, then drop me an email and I will forward
or
that to
email me directly. I'm sure you can find me online somewhere.
Yes. Okay.
Alrighty.
Yeah. Okay. Usually we applaud. So thank you very much again for your very nice talk. And yeah, then our next talk will be on next Friday. And yeah, see you soon.
See you.
Thank you very much for your attention, and bye-bye.
Thanks for coming. Bye-bye.